So yeah, we're going to prove this theorem, right? So yeah, so we remember Erdős-Corrado, right? The biggest intersecting family has size n choose k minus 1, or sorry, n minus 1 choose k minus 1. This is kind of related, right? We want to find the smallest number of intersecting families for which you can partition n choose k. Or in other words, you want to color n choose k so that every color class is intersecting, right? And we saw an example last time using n minus 2k plus 1, or sorry, plus 2. And we're going to show that you can't do it with fewer. So recall this example, right? So if we let fi be the collection of things in n choose k where I is the minimum element, then so if I take just f1 up to f n minus 2k plus 1, and then I take all the remaining sets, so this partitions it. So this partitions n choose k into n minus 2k plus 2 intersecting families. Okay. And briefly, like the idea here was f1 is all the sets that contain 1. So that's intersecting. And then you take f2, which is all the things that contain 2 but don't contain 1, but they all contain 2, so that's intersecting. And you keep doing that. Like each time you do that, if I take the sets that contain 1, and then I look at everything else, well, those are the sets that don't contain 1, so they're in a smaller ground set from 2 up to n. You keep doing this until the size of the ground set is 2k minus 1. And at that point, everything intersects because by pigeonhole. So that's this last collection. Yeah, if you think about it, everything here intersects because they're all subsets of a set of size 2k minus 1. Anyway, we kind of went over that last time, so I might be quick with that. So I mentioned last time we're going to prove this using topology. I also said you shouldn't worry too much about topology, so I am going to build up everything we need here. I should also say this is kind of, in some sense, this topic is sort of not really testable in some sense. Like, I don't think there are any, unless I forgot about it, like I don't think there are any assignment questions on this. So this is kind of just for your enjoyment, or, well, yeah. So you don't have to worry about, you don't have to necessarily enjoy it if you, but yeah, you don't have to worry about this showing up on an exam. The open book exam. Okay, so let's kind of talk about spheres. So for D at least 1, so I'm going to use this notation. I'll write like a blackboard, S, D. So that's the D-dimensional sphere. So what I mean is that this is the set of all points in R to the D plus 1, where the distance from that point to the origin is equal to 1. So the norm, so this is just the Euclidean norm, like the distance or the length of the vector. So it's equal to 1. So for example, S1 is a set that lives in R2. And it's all the things, distance 1 from the origin, right? And then S2 is what you really think of when you think of a sphere. It's, it kind of lives in three-dimensional space, but we call it S2 because, you can think of it, it's kind of a two-dimensional object in some sense, right? S1 is kind of one-dimensional. It's just a line that goes around the origin. But yeah, it lives in kind of a one higher dimension, right? Stop me at any point if you have questions. Okay, so we've got spheres. Now I want to talk about hemispheres, which is just what you get by chopping a sphere exactly in half, right? So, and specifically, I care about open hemispheres. So for a point, the open hemisphere centered at X is the set H of X, which I'll define as it's the set of all Y in the sphere where, basically you want it to be on the same side of the sphere as X. Like you think about an actual, like the globe, right? You have the North Pole, which is a point on the sphere. Think of the globe as a sphere. You have the northern hemisphere. That's like the stuff above the equator, right? So if we think of X as being like the North Pole, H of X, like if we now think of the equator, X could be anywhere on the sphere, but now think of the equator as being, think of X as the North Pole, then the hemisphere centered at X is everything on that side of the equator. Technically, so maybe a way I can define this, it's not clear why this is right, but it's all the things where if you took the dot product with X, it would be positive. Because, yeah, the equator would have dot product 0 because it's orthogonal to the North Pole. Things in the southern hemisphere would have negative dot product. This would have positive dot product. But anyway, just think of it as like, if I've got this circle, I've got a point here. It's all the things. So if I drew a line orthogonal to that vector, it's all the things on this side. Is that clear? Any questions about that? Yeah, good. And then this definition kind of came up last time. So point, if I have 2 points, x and minus x on SD, we say that these are antipodal. Or antipodal. I don't really know how you're supposed to pronounce this word. I just read this word, right? I don't usually say it, but yeah. I'll keep saying antipodal, unless, actually, maybe we should have a vote. Like, who wants me to say antipodal or antipodal? I don't know. Antipodal seems better? Okay, fine. But yeah, this is like, now this is kind of thinking if x is the North Pole, then minus x is the South Pole, right? Opposites on the sphere, right? Now here's a fact that's going to come up. If I take x and y in the sphere, so for x and y in the sphere, if I look at their open hemispheres, well, the only way they can be disjoint is if x and y are antipodal to each other, right? Yeah, definitely the north and south pole, their hemispheres, because we're not including the equator, right? So yeah, those are disjoint. And if I just move one of those points a little bit, then definitely the hemispheres are going to touch, right? So that's somehow going to be important. So now a bit of topology. So if I take a subset of the sphere, or actually no, sorry, let's say this in another way. So I'll phrase this as follows. So the open sets in the sphere are defined as follows. So so any open hemisphere is open. If U and U prime are open, then their intersection is open. And thirdly, if I take a bunch of open sets, U1, U2 up to, if I take countably many, then if I union all of them, or sorry, yeah, union, yeah. If I union all of them, then that's open. I mean, actually, we're not going to need anything. We're really not going to need anything at all deep about topology here. Like, I mean, if you haven't seen topology before, topology is just asking, you have some set, and what are the open sets, right? Yeah, so all we're going to need is that, like, open sets are closed under, if you take intersections of two open things, they're open. You should think of like intervals in the reals or something, right? You have two, well, so yeah, in the reals, basically, it kind of, your open sets are kind of generated by open intervals, right? Anyway. So like in the one-dimensional sphere, basically you should kind of think of these open sets as being kind of like a bunch of open intervals on the sphere or something like that. Okay. Any questions about any of this? Yeah. Yeah, that's a good, actually, yeah, it's kind of useful to think about. So yeah, what you should think about in S2 is maybe you've got like it could be like a region kind of on the, on the surface of the globe, but not including any of the boundary points. So kind of like an open interval is like a kind of region of a one-dimensional thing without the boundary. You also want that kind of thing in here. So this is like an open set, or you could have a union of these things, right? So I could have a blob over here and a blob over here of, yeah. Yeah. So you should just visualize kind of shapes on the sphere, but without any boundary on them, like the boundary's missing. Any other questions? And then once you know what open sets are, a closed set or yeah, well, is the complement of an open set. And these are going to be analogous to kind of closed intervals, right? It's going to be, you should think of kind of regions here where it includes all of the boundary. A set where, for example, you, like on the one-dimensional sphere, if you have like an interval here that has one boundary kind of closed and one open, that's not closed, that's not open, it's neither, right? So you're not, you know, if you want to do an open set, you can't include any boundary. If it's a closed set, you have to include all the boundary. Okay. Any questions at this point? Okay, so yeah, let's now state kind of a important lemma. And this is going to describe all the topology we need for this proof is in this lemma. So if I take, so if U1 up to U d plus 1 are subsets of the sphere such that each of the first D sets have to be open or closed, but I don't actually care about the last one. So each of U1 up to UD are either open or closed. Okay. And just to clarify, different sets could be different like things. So U1 could be open, U2 could be closed, U3 could be closed, U4 could be open. Like each of them individually has to be open or closed. Then one of these sets contains a pair of antipodal points. So there's some I between 1 and d plus 1. And a point x in the sphere such that x and minus x are in ui. Okay. Totally unclear how this can connect to intersecting families, right? Like, how am I going to use this to prove this theorem? But yeah, that's why this is such a genius kind of proof. Yeah, in terms of intuition about this, right? Like, I think thinking about the case d equals 1 is nice for intuition. Like, if I wanted to, I want to cover just the circle with two sets. So the first set has to be open. The second set can be anything, although it's going to be the complement of that set, so it's going to be closed. But how could you cover it without including antipodal points? If you think about it, you just can't do it. Yeah?
You're missing a condition.
Oh. Yeah, okay, these could all be the empty set at this point. Yeah, thank you. So the union of these sets, sorry, thank you, yeah, is SD, and yeah, that's quite important. They have to cover the sphere. Otherwise, they could all be empty, and definitely they don't contain antipodal points. Okay. So yeah, if you think about it in the case like d equals 1, you know, I feel like the most natural thing to try is to take like some kind of open hemisphere thing, right? You're going to contain a lot of the thing, but without antipodal points. But then the complement is going to contain those antipodal points. So like you can't, no matter what you do, like it just doesn't. You just can't do it without. So anyway, if we've got time at the end, I'll prove this. I'll derive this from another topological result, which we won't prove. But yeah, let's just kind of assume this for now. Any questions about this statement? Okay. So let's prove the theorem of Lovász. So we're going to do this by contradiction. So I'm going to let D be this number n minus 2k plus 1. So we're assuming there's no partition with this many elements, right? And so if I'm going by contradiction, I'm going to let D be this and assume, and suppose F1 up to Fd are intersecting and they union to the entire n choose k. Okay, and we want to get a contradiction. Now, how do we get the sphere into this? So basically, so I've got this ground set, the numbers 1 up to n. I kind of want to represent those numbers 1 up to n by points on the sphere. Okay. I'm not going to be, I don't have to be very careful how I do this actually. I'm just going to randomly map points to the sphere and call those like x1 up to xn. So pick x1 up to xn in the sphere of dimension d. We're going to at some point need to remember like d is this special number, n minus 2k plus 1, randomly. So when I say randomly, I don't mean arbitrarily. I don't mean like in any way you want. I mean actually like pick a point, like just throw a dart at the sphere, right? Wherever it hits, you put a point. Throw another dart. Wherever it hits, you put a point. Just do it actually randomly. Well, the thing is, if you do it randomly, the chances that two of them are the same is going to be 0. Yeah. Yeah, actually, there's this whole randomness. Basically, I want these points to be kind of independent in a sense. So yeah, if I picked it arbitrarily, you could end up having 2 points being the same. I'm doing it randomly, so you're never going to have that. And there's also other things you're never going to see, right? Like if I take, like for example, what's the chances that 2 of these points are antipodal? Well, it's 0 because I pick 1. What's the chances I hit? Like I've got kind of infinitely many choices here. Like what's the chance I hit exactly the opposite one, right? It's going to be 0. So there's various kind of relations that like any kind of algebraic like relation you might want these things to satisfy. Like, yeah, they're not going to, satisfy them. Okay, but that's going to come actually into play at the end. Okay, so now we need to bring in some topology. So I'm going to, let's see what happens. So for each I between 1 and d, let ui be the set of all points in the sphere. So not necessarily these x1 up to xn. These are just general points in the sphere, such that there exists a set in fi such that all the points xj are in the hemisphere centered at x for all j in A. It's kind of a mouthful. But here's the key question to ask about this. Can ui contain antipodal points, let's say x and minus x? And if not, then what would be the kind of contradiction? Like, what would be the problem? Anybody online see anything? Or anyone in the room? Apologies. This statement is kind of like, seems slightly ugly, but see, what if there's some x and a minus x in ui? Yeah. Yeah, that's the contradiction is about being an intersecting, hi being an intersecting family. So yeah, can you say that, like flesh that out anymore, or? Okay. Yeah, so imagine like, yeah, x is kind of the north pole, z is, or minus x is the south pole, right? This is saying that, oh yeah, maybe somebody was, I'm not sure, okay, maybe, yeah, I'm hearing things. Right, so what does it mean for x to be in ui? And let's say x is just, yeah, like kind of the north pole of this thing. That means that there's a set A in fi where all of the points xj corresponding to elements of A are in the hemisphere of x, like centered at x. So all of these points xj, where j is in A, are in the top half of the sphere. So maybe I'll write little squares here or something to mean these are the points xj for j in A. And yeah, they're all on the top half. But for minus x to be in ui, that means there's another set in fi, let's call it B or something. So these are the points xj for j in B. And for minus x to be in this set, it means that, yeah, there's some set in fi where all the points corresponding to elements of that set are in the hemisphere containing minus x. But then these hemispheres are disjoint. So that means that these points, these squares up here, none of them are the same point as any of these triangles, right? So it's telling me that xj such that j is in A is disjoint from xj where j is in B. So that implies A and B are disjoint. But that contradicts the fact that Fi is intersecting. I know that's kind of illegible at the bottom of the board, especially for you guys over there. But any questions about that, or do we do you see how that works, right? This kind of x being in UI kind of pulls there's some set A where everything in A is up in this hemisphere, but then there's some B in Fi where everything's in this hemisphere, but then they're disjoint. That's the key thing about this intersecting condition. Okay, so all of these things UI, they can't contain any antipodal points. Let's observe that these sets UI are open. So how would I get that? Well, remember, an open set is just something I get from a bunch of open hemispheres by doing intersections and unions, right? Countable unions, finite intersections, but everything is actually going to be finite here. So, now a key thing is to observe that UI is actually equal to a union over all A and Fi of an intersection over J and A of H of Xj. H of Xj is, remember, the hemisphere centered at Xj. Okay, and the reason I'm writing this is to make sure that, so because I can write it as a bunch of hemispheres with intersections and unions, it has to be open. This requires a bit of justification. So the key observation here, if I have 2 points x and y, to say that y is in the open hemisphere of x is the same thing as saying that x is in the open hemisphere centered at y. So if I say I fix this A, saying that xj is in H of x for all j is the same as saying x is in the hemisphere. Yeah, so this for all j and a is the same as saying x is in H xj for all j. Right? Because these two statements are the same. You can switch the two things. So that's like saying x is in the intersection over all j of H of xj. And then this exists in A statement is just a union, right? We just say we union this over all the possible sets A. And that's kind of dealing with the there exists an A such that. So yeah, there exists an A such that xj is in the hemisphere containing or centered at x for all j, and that's the same as switching these two things around, and that's the same as like putting an intersection here. Does that make sense? But the key thing is that this thing is open. And why do I care about that? It's because I can use this lemma now, right? So now I'm going to just define ud plus 1 to be everything left over when I delete u1 up to ud. So yeah, we check our conditions of this lemma, right? u1 up to ud plus 1. They're all subsets of the sphere. Their union is equal to the sphere because of how I defined ud plus 1. For the first d of them, they're all open. So they're open or closed. So there must be an index where ui contains two antipodal points. But we know pretty much none of them do, right? We already proved that ui for I from 1 to d doesn't contain antipodal points. So the only choice left is d plus 1 must contain them, right? So if we can rule that out and get a contradiction, then we're done. So by the lemma, there must be x and minus x in ud plus 1. Okay. Right. So here's the thing. Like we've kind of used, we've used the hypothesis. Like we've used the property that each of these things are intersecting, these FIs. One thing we haven't used is this fact that they partition n choose k. Right. That's never come up in the proof yet. So that's what we need to use to settle this case. Okay. Maybe I'll. Okay, so here's a question now. So can it be the case that k of the points x1 up to xn are in the open hemisphere centered at x, where x is this x? It's chosen so that it's, so that these antipodal things are in ud plus 1. Actually, though, we're not really going to use minus x for this. And like this is going to, x is in ud plus 1. Can k of those points be, is it possible for them to be in the open hemisphere containing or centered at x? Pretty much always when I ask you a question, the answer is no, right? Like, it's not going to be possible, but I guess the question is why? Any thoughts? It's maybe a bit of a subtle issue here. It's again coming down to this fact that if y is in the open hemisphere centered at x, then x is in the open hemisphere centered at y. So if there are k points among those x1 up to xn that are in that hemisphere, then x is in the intersection of all of their hemispheres. K points and x is in the intersection of all of their hemispheres. Well, that set of k points, it must correspond to one of the sets A. Like it's a set A of size k. It corresponds to set A of size k. But that A must be in one of the FIs because the FIs cover the n choose k. So yeah, I guess the answer is no. So let me kind of write that out. So if there were, let A be a set of k indices such that xj is in hx for all j and a. So that implies that x is in the intersection over all j in a of h of xj. And now since the F1 up to FD collections cover n choose k, there must exist an I such that A is in Fi, but then therefore this would tell me that X is in Ui, but that's not possible because X is in UD plus 1, which is the complement of like, so that's a contradiction. So X can't be in UI because it's in UD plus 1. UD plus 1 is literally the complement of all the union of the UIs. So there exists I should say, between 1 and D. It's a really subtle contradiction, I think. But any questions about that? Okay. So similarly, so there cannot be k points of these points in the hemisphere around x. Similarly, there can't be k points in the hemisphere around minus x. Right? But where else can the points be? Like, these two hemispheres pretty much cover everything, right? Except for this like one thin line around the equator. So everything else has to be right on the equator. Without maybe thinking too deeply, but like, can anyone see why that's probably not going to happen? To have like a lot of, if I take 2 points, like a north and a south pole, why would I not see like lots of points on the equator? Yeah, exactly, right? You'll see a certain amount, you could see a certain amount of them on the equator, but you're not going to see a lot of them because, yeah, you chose them randomly. At some point, this is going to have like a 0 probability. So, so yeah, to just finish that and flesh that out, so similarly, H minus x contains at most k minus 1 points from x1 up to xn. So basically, the hyperplane, like, I'm just writing the things on the equator. So the set of all y, and let's just say an Rd plus 1, such that y, x, they have 0 dot product, contains at least n minus 2 times k minus 1, so which is n minus 2k plus 2, which is d plus 1 points from like this set x1 up to xn. Okay. So that's like technically that's how many it'll contain. And this, like I said, this is just you should really just think of this as the equator. when you take x and minus x, this is the thin line. Well, okay, this is actually I've made the whole kind of plane, but really they have to lie on this thin line between the two. Right. We can think about why this is unlikely, and it's exactly what was mentioned. So, like in the case d equals 1, right? This would mean that when you pick your n random points, that 2 of them are antipodal, because they would, that's the only way to be on the, the equator between x and minus x is to be antipodal, right? That's going to happen with probability 0. Similarly, yeah, if you think about, what's the chances, I pick n points at random in a sphere, like a 2-dimensional sphere, that you're going to see 3 of them that are kind of contained in the same great circle. That's not going to happen. 2 of them, yes, because any 2 of them, you can actually just make a kind of great circle around them. But to get 3 of them, that's just not going to happen. Because any 2 of them kind of define a unique, like, great circle. So yeah, this occurs. So maybe let's not worry too much about the actual details, but so this occurs with probability 0. So in other words, it doesn't happen. So this is a contradiction. And it completes the proof. Yeah, don't ask me how anyone came up with this. This is this is one of the great proofs in combinatorics, I think. Any questions about any of that? Yeah, so I don't really have time. I was thinking of deriving that topological lemma from another topological statement called the Borsuk-Ulam theorem. Maybe I'll just write that theorem, but I won't use it to prove the lemma. But it's worth just like being aware of it for your own mathematical background. So the Borsuk-Ulam theorem. So for any continuous function f from a d-dimensional sphere to Rd, there exists antipodal points x and minus x such that f of x equals f of minus x. Okay. Might not be obvious why this implies the lemma, but it maybe has a feeling that there's probably there's some relation here, right? That here we're looking at antipodal points, and that other lemma was talking about antipodal points. There's something connected there, but yeah. Okay. But yeah, in the notes, there's actually if you're interested, there's a derivation of that lemma from this theorem.